Welcome to Episode 14, Reliability, Predictability, and Performance. In the cloud, reliability is more than uptime. It's the foundation of user trust. When an application consistently works as expected, users stop thinking about the technology and simply rely on it. Reliability is the feeling of confidence that the service will respond correctly every time, even under pressure. Azure and other cloud platforms offer tools and design patterns to build that confidence, but reliability ultimately depends on thoughtful architecture and disciplined operations. Predictability and performance sit alongside reliability. Predictable systems behave consistently, and performance systems do so quickly. Together, these qualities define how dependable your service truly feels to those who use it. Failure domains are one of the most important design concepts behind reliability. A failure domain is a boundary within which problems can occur without spreading outward. In Azure, these domains might be a virtual machine, a rack, an availability zone, or an entire region. Limiting the blast radius, how far the impact travels, keeps small issues from becoming full outages. For example, deploying across multiple zones ensures that the failure of one doesn't affect the others. Designing with failure domains means asking, if this component fails, what else breaks with it? The goal isn't to eliminate failure, it's to contain it quickly so recovery is faster and users stay confident. Predictable throughput and latency come from planning, not luck. Throughput measures how much work a system can do in a given time. Latency measures how long each request takes. Together, they shape user experience. Azure provides monitoring and auto-scale tools to help maintain consistent performance under load. Budgeting for latency means deciding in advance how much delay is acceptable for each operation. For example, a chat message may tolerate 1 second of delay, while a financial transaction may require milliseconds. Predictability comes from designing limits into your system so that even under heavy demand, performance degrades gracefully rather than collapsing. Performance baselining starts by measuring how your system behaves under realistic conditions. Synthetic tests and lab simulations provide insight, but nothing replaces observing real workloads in production. Establish a baseline for normal response times, CPU usage, and throughput. Once that baseline is clear, deviations become meaningful signals rather than noise. If response times start drifting upward, you'll notice early and adjust before users feel pain. Performance baselining turns intuition into data and makes performance management a repeatable discipline. It also guides capacity planning, helping you predict how changes in traffic will affect your service. Caching is one of the simplest and most effective tools for improving both performance and reliability. By storing frequently accessed data in memory or at the edge, caching reduces the load on your core systems and lowers latency for users. Azure provides multiple caching options, including Azure Cache for Redis and content delivery networks for global distribution. Application-level caching handles repeated queries or computations, while edge caching accelerates static content like images and scripts. Together, they smooth out demand spikes and keep user experiences consistent. The key to good caching is knowing what to store, how long to keep it, and when to refresh it automatically. Queuing, back pressure, and smoothing spikes are techniques for handling unpredictable workloads. Instead of overwhelming a service by sending all requests at once, queues accept them at a controlled rate and process them when resources are ready. Azure's Service Bus and storage queues provide managed solutions for this pattern. Back pressure occurs when downstream systems signal that they're full, allowing upstream components to slow down gracefully instead of failing. This cooperative flow control keeps systems stable under stress. By shaping traffic through queues and rate limits, you convert chaos into order and transform sudden bursts into steady, manageable workloads. Retries, timeouts, and idempotency are the safety nets of distributed systems. When a network call fails, a retry gives it another chance to succeed, but only within a reasonable timeout so it doesn't hang forever. Idempotency ensures that if the same operation runs twice, the result remains correct, critical for financial or transactional systems. These safeguards handle the messy reality of networks where temporary errors are common. Azure SDKs and API guidelines encourage developers to implement these patterns automatically. Done well, retries and timeouts protect users from seeing transient failures and make systems resilient against the small but inevitable imperfections of connectivity. Chaos engineering takes resilience to the next level by testing failure intentionally. Rather than waiting for outages, teams introduce controlled disruptions, such as shutting down a node or injecting network latency, to observe how the system responds. Azure's Chaos Studio supports this discipline safely within your environment. The goal is not to cause harm, but to learn. Does the system recover as expected? Do alerts trigger properly? Does user experience remain acceptable? By practicing failure in daylight, you ensure that real incidents at night are less surprising. Chaos engineering turns reliability from theory into practiced confidence. Capacity modeling and load testing validate whether your design scales predictably. Modeling uses historical data and growth forecasts to estimate future demand. Load testing confirms those estimates by simulating users or transactions at scale. Azure load testing provides a controlled environment for these exercises. The goal isn't to reach failure, it's to discover where limits begin so you can plan ahead. Understanding how performance degrades near capacity helps you set autoscale triggers and capacity buffers intelligently. Without testing, scaling decisions are guesses. With testing, they're informed, reducing risk and ensuring smoother growth over time. Service Level Objectives, or SLOs, and Service Level Indicators, or SLIs, formalize reliability goals. An SLI measures a specific aspect of performance, like request success rate or latency. The SLO defines the target, such as 99.95% success over 30 days. Error budgets express how much unreliability you can tolerate before corrective action is required. Together, these metrics align teams around measurable outcomes rather than vague aspirations. They balance innovation and stability. Teams can release new features as long as error budgets allow. SLOs create shared language between engineers and management, transforming reliability into an accountable, transparent process. Alerting systems must be tuned to user impact rather than technical noise. Not every metric deviation deserves a page at midnight. Focus alerts on conditions that users would actually notice, like failed transactions or elevated response times. Use thresholds that distinguish between minor fluctuations and real degradation. Group related alerts to reduce duplication, and design runbooks that tell responders what to do next. Azure Monitor and Application Insights allow flexible alerting tied directly to business metrics. When alerting aligns with user experience, teams stay responsive without burning out. The goal is not more alerts, it's better ones that matter most. Post-incident learning is where reliability improves the fastest. Every outage or slowdown is a chance to uncover weak assumptions or process gaps. After incidents, conduct blameless reviews that focus on understanding, not punishment. Document what happened, what signals were missed, and how detection or recovery can be improved. Build runbooks that guide future responses step by step. Over time, these runbooks become institutional memory that reduces recovery time and anxiety. The value of an incident lies in what you learn from it. With disciplined reflection, even the worst outage becomes fuel for resilience growth. Continuous improvement cycles turn reliability from a project into a habit. Review metrics regularly, revisit SLOs, and adjust designs as patterns change. Automate feedback loops between development, operations, and business teams. Small, steady improvements prevent major surprises later. In the cloud, change is constant. Services evolve, dependencies shift, and workloads grow. Reliability must evolve alongside them. Embedding improvement into your process means you never fall behind. The best systems aren't perfect, they're simply improving faster than they decay. This mindset keeps performance and predictability aligned with real-world needs as technology advances. Predictable performance habits combine all these ideas into daily practice. Measure what matters, design for containment, and rehearse recovery. Use caching, queuing, and autoscaling as instruments of control. Treat incidents as data, not disasters. The cloud provides infinite capacity, but reliability still depends on human discipline and awareness. When teams build predictability into their culture, monitoring carefully, responding calmly, and learning continuously, systems earn user trust by design. In the end, reliability is not only about technology, it's about the steady habits that keep promises made to users every single day. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.